Let's now look at combinations. Now, combinations is still a set of objects, but now we're not actually concerned with how they're arranged. That's no longer important. So it's more a selection of objects rather than an arrangement of objects. We're going to arrange them in a line, but now the order is not important. So as far as we're concerned, AB is the same as BA. We don't really care the order. They're the same objects. There's no point in looking at the case where we use all the objects, because clearly there's only one way then if we're not concerned about the arrangements, and that's we have all the objects. Let's have a look what's happening with something like this. If I've got 5 objects and I'm just going to arrange 2 of them, right? So that would be a permutation, of course. And there's all the different permutations, and we know that ends up being 20. But if I'm not concerned with the arrangements, then some of these are now the same. So BA is the same as AB, and so on and so on. So let's just get rid of the ones that double up. How many am I left with? I'm left with 10. But more importantly, how did we get 10? We had 20, but now we're not concerned with the arrangement. So that idea again, that we'll just divide by the number of ways we could arrange those objects. And the number of ways we could arrange those objects is 2 factorial. So 20 divided by 2 factorial, we get 10. Now just to highlight that that does indeed work, if I have 5 objects and I want to arrange 3 of them, so there are 60 there, but we have double up. See, ABC, same as BAC, CAB, and ACB, and BCA, and CBA, and then BAD is the same as DBA, and ADB, and BDA, and eventually get rid of all those doubling ups. And we've been left with 10, and 10 is 60 divided by 3 factorial, so it seems to confirm that idea of, hey, all we've got to do is divide by the number of ways of arranging those objects. If we have n different objects then, and we only want to grab k of them, we're not interested about the order, then it would be npk, that would be the permutation, but I divide by the number of ways those k objects could be arranged, k factorial. So we end up with this as a formula. N factorial over n minus k factorial, k factorial. So it's really nice because have a look at the 2 things on the bottom, they actually add together to give the number at the top. There is a notation for that one as well, C for combination, NCK on your calculator, then that's on the division button. How many ways can 6 numbers then be chosen from 45 numbers? Now this is the basis behind lotto, those sort of games. You know, when the balls come out, we don't care about the order the balls come out of the machine, we just want to get the same numbers and win a lot of money. 45, I want to get 6 of them. So 45C6 turns out to be, what's that? 8,145,060. Now of course if you're very patient, you want to fill out enough coupons and guarantee a win. Last time I checked, I think it's about 70 cents a game. So to pick one combination costs you 70 cents. So if you wanted to cover every possible combination and you happen to have a spare $5.7 million lying around, you could put every single possibility, cover it all, guarantee you win that prize. How much is that prize going to be? You know, some of those weeks when they're like 100 million and things like that, you think, wow, if I had 5.57 million, I could guarantee a win of 100 million. Mind you, if you've got 5.7 million, why would you be bothering gambling to try and win 100? Maybe you could. Of course, the downfall, there is still a gamble involved, even if you do cover every possibility, because the way it works is if someone else happens to get it as well, you have to share the prize. So you don't want too many people getting all the possibilities there. Committees of 5 people attained from a group of 7 men and 4 women. How many committees are possible? Okay. Well, we're choosing from 11 people. I just want to get 5 of them. Again, gender doesn't matter. 462 committees. What if we said, no, men only? Once upon a time they used to do that. 7C5 then. So we've narrowed it down and now we've only got 21 possibilities there. That's not really fair. What about if we said, well, you've got to have at least 1. And this is where we can use our complementary event idea. Well, I know all the possibilities. I know how many are only male, therefore all the ones that are left must be the ones that have at least one female. So that idea from probability we could use again. A lot of card games involve the dealing of 5 cards. So we're going to deal 5 cards from a 52 card deck. How many different possible hands are there? And of course in cards we don't care the order the cards come to us. You just pick up your hand, there are your 5 cards. So it's a combination. 52C5 turns out to be that, 2,598,960. What's the probability of getting 3 of a kind? So in the game of poker, that's a kind of hand you could get. Let's work out how many ways we could get 3 of a kind. So the first thing I've got to work out is which 3 are they going to be? There's 13 different values we could have in the card deck. We're saying which one of those is going to be the 3 of a kind. That's my first choice there. 13C1. Now once I've decided that, then, well, there's 4 of those cards in a pack and I want to get 3 of them. So times 4C3. I now need another 2 cards. There are 48 cards left to choose from. Even though I've only selected 3, which leaves me with 49 cards, I don't want the other. Let's say it was aces. Say I wanted to get 3 aces. I don't want to get the 4th ace, because otherwise I wouldn't have 3 of a kind. I'd have 4 of a kind. Reality is I probably would like to get the 4th one because it's going to be a better hand, but for the sake of this question, I don't want to get that 4th one. So 48C2, which gives me 58,656. Brings up the question, what's the probability of 3 of a kind, which is what they wanted us to solve. That simplifies down 94 and 2,915. Sometimes to get a better feel of how likely something is, we change it to a percentage. That's around 3.2%. 3.2% chance. We're going to pick a team. It's a 4-person team. How many ways can we pick our team? From 16 people, we're going to choose 4. 1,820. Okay. What's the probability that it's all 4 women in our team? From the 9 women, I'm going to choose 4. I get 126. So the probability, 126 on 1820, which is 9 on 130. Let me talk about dividing into groups then. So look at some cases. If I've got m plus n objects, and I'm going to divide them into 2 groups containing m and n objects. So 2 groups. The number of selections would be m plus n. That's the total amount I'm choosing from. And I'm going to choose m of the objects. Now once I've chosen that, automatically I've now got the other group as well. So it would end up being m plus n factorial on m factorial n factorial. Look at that. On the top of the fraction, I've got the number of ways of arranging the m plus n divided by m factorial, the number of people in that first group, n factorial, number of people in the second group. So it's, hang on, that's looking very much like another type of question that we saw. It's back to that when we have some objects the same. And if you think about it, it is the same, because rather than just saying I'm going to choose them, let's say they were labelled, and Team 1, if you like, all has the label M, and Team 2 all has the label N. And so amongst all these people, they're either going to be an M or an N. In other words, how many ways are there of forming up an arrangement of letters where I have M's and N's? It will be that. Because that now brings me to, let's push that idea further. Dividing a group of 2 M objects into 2 groups, each of them now contain M objects. This is where I've got to be careful. It's not going to simply be 2m factorial over m factorial m factorial. I've now also got to divide it by 2 factorial. Because unlike the first one where I said, hey, it's the same as forming these words, because the groups are of different size, I can do that. But if the groups are of the same size, I need to divide by the number of ways I could arrange the groups. Because imagine this selection. I could have A, B, B, B. But I could also have B, 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 and A. Now, as far as we're concerned, they're the same, because we're not actually interested in that. So if they are the same size groups, I need to divide by the number of groups, factorial. So we divide by the number of ways the groups of the same size could be arranged. So I actually end up with 2m factorial on m factorial, 2 factorial. Dividing a group of m plus n plus p objects into 2 groups of m objects, n objects and p objects. Now, of course, it's 3 groups. Let's look what happens here. So I'd start off and say, of the m plus n plus p objects, I'm going to choose m of them. But now I'm left with n plus p objects, but I'm going to choose n of them. And then I've automatically got the third group. If I play around with the formula, I get some cancelling there. You see the n plus p factorial cancels. And once again, I end up with m plus n plus p factorial over m factorial, n factorial, p factorial. The number of ways I could have arranged those objects if I was interested in that. So again, it's like the word problem. Let's apply that then. How many ways can I get 15 students and divide them into 3 equal groups? I now don't actually have to use combinations for this. I can think of it like that word problem. So it would be 15 factorial over 5 factorial, 5 factorial, 5 factorial. However, the groups are of the same size, so I'll also divide by 3 factorial. And we get the answer, there it is, 126. 126. A restaurant has 3 tables. Each of the tables has got 4 seats. 12 people arrive. How many ways can we arrange these people? Go and sit down to your tables. Okay. 12 factorial over, each table's got 4 seats. 4 factorial, 4 factorial, 4 factorial. The groups are of the same size, so 3 factorial. So what I have done is I've now divided them into 3 groups. But this question now has an extra thing, because now I'm going to actually do something with the groups. I'm going to place them on tables. So I have to now multiply by 3 factorial the number of ways they could be arranged on the tables. So group 1 could go on table A, group 2 could go on table B, group 3 could go on table C, or group 1 could go on B, group 2 could go on A, group 3 could go on C. They are now different. So I have to multiply by the 3 factorial. So effectively, what have we done? Notice 3 factorial will cancel with the 3 factorial. So really, if we're then going to arrange those groups and do something with them, I don't need to divide by the arrangements, because now the arrangements are important. So it's the difference between just, hey, I'm going to pick groups, or I'm actually going to do something with the groups. That brings up this idea. When you think about what it is, all a permutation really is a combination multiplied by the number of ways the objects can be arranged. So another way of thinking about it is to, hey, if I've got this more involved problem, what I could do is I'll select the objects first, then I'll go and arrange them. That's really what a permutation is. I've chosen the objects, I've selected them, then I go and arrange them. Now, an idea, a method for solving, known as the insertion method, way of approaching a problem like this, when some of the objects are not allowed to be together. The letters, this may have even been a question in one of the exercises, I think. The letters of the word between are arranged in a line. How many ways can they be arranged if all the E's are separated? Well, the traditional way is I'd look after the restriction first. I'd go, how many ways can the E's be placed? They say, well, here's all the spots I could put them. Now they have to be separated. So I could put an E in the first spot, then the next one in the third spot, and then the third one could go in the 5th spot. But hang on, the third one could also go in the 6th spot, or it could go in the 7th spot, and they'd still all be those 3 E's would be separated. But I could have put E in the first spot, and how about I put E in the 4th spot, and then I could put E in the 6th spot, but it could go in the 7th as well. So there's 2. Or how about I do this? E in the 1st spot, and then I'll have the 2nd E over here in the 5th spot, which means the 3rd E has to go in the 7th spot. So there's only one way of doing that. Of course, all of those assumed I put E in the 1st spot. What if I put E in the 2nd spot? Again, I could work out, well, there's 2 ways there. But if I do it that way, I could get 1. But what if I put E in the 3rd spot? So the first one's now going here. There's another 1. And eventually I come up with 10 possibilities for the E's. So the total number of ways, arrange the other letters, 4 factorial, and we get 240. And that's how we can tend to do it. Here's the idea. We do it by inserting. So actually, we're going to place the E's last. If I arrange the other letters first, so the B, the T, the W and the N, arrange them first. There's 4 factorial ways of doing that. Now what has happened is we've now created 5 spots for the E's to go in. So I am now going to insert the E's into those spots. And because I've placed the spots with the B, T, W, N, the E's will then be separated. Now, they can go anywhere because they're the same thing, so the order's not important. So there's 5 spots, I'm going to use 3 of them. 5C3, 240. We get the answer much quicker than trying to work out how many ways can we place all those E's. If we'd said something like this, well, actually, exactly 2 of the E's are together. Again, I place the other ones first. I've got 5 spots, but it's 4 factorial times, but now the objects are not the same, because if 2 of the E's are together, one of my objects is EE, and the other object is just a single E. So now the arrangement is important. It becomes a permutation rather than a combination, because they are different objects. So this time I multiply it by 5p2, and there would be 480 ways of doing that problem. Next idea. The idea of separators. This idea is good when we want to divide large groups into smaller groups, so the grouping idea. Here's a question. 3 pirates are sharing out the contents of a treasure chest. It contains 48 gold coins and 2 lead coins. They're going to divide up the treasure, but these are the rules. The first pirate comes along, you can just keep taking as many coins as you like. But as soon as you take a lead coin, your turn's up. And then the second pirate, you can now do the same. You can take as many coins as you like until a lead coin comes, your time is up. And then the third pirate, you just get whatever's left over. How many ways could we distribute those coins? If we think of this question, it now becomes, again, equivalent to the word problem. So I'm going to make the letters of our word, I'm going to have 2 L's for the lead coins and 48 G's. And really all I'm now saying is I'm just going to arrange all these things, and then the pirate just walks along the line. If it's a G, I'll pick it up, I'll pick it up, I'll pick it up. Oh, L, I got to stop. Then the next pirate comes along. If it's a G, I'll pick it up, I'll pick it up, pick it up. I get to an L, I stop. So the L's, if you like, are acting as a separator between each of the pirates' share of the treasure. Well, it's 50 factorial and 48 factorial, 2 factorial, 1,225 ways of doing that. It actually was similar. 2012, this one came up, and I thought, wow, that's really similar to what we did. How many ways can 10 identical coins be allocated into 4 different boxes? Okay, again, whilst they haven't said lead coins in this one, I'll just say S for separator. There's going to be a separator. So I'm going to arrange 10 C's, the coins, and 3 S's, and they will act as the separator of the boxes. So it's like we've got a box of coins, however many are in there, then we have our separator. We have our next box of coins, and we have a separator, and so on. So again, it's like just arranging them up, and that's telling us what's going in the first box, what's going in the second box, and so on. All right, well that makes the question straightforward. I've now got 13 objects I'm arranging. There are 10 C's, and there are 3 S's. So 13 factorial and 3 factorial, 10 factorial, which is 286. The interesting thing is only 1% of the state got that question correct. Only 1% of the state. Let's have a look at this one. A hostel has 4 vacant rooms. Each room can accommodate a maximum of 4 people. 6 people come along. How many ways can they be accommodated in this hostel? The total number of ways, if there were no restrictions, each of those people would come along and they got 4 rooms to choose from. It's our basic counting idea, 4 to the power of 6. That's if there was no restrictions whatsoever. But we have to take away the possibilities that can't happen. We cannot have all of them in the one room. because it said maximum of 4 people in a room. So I've got to take away all the possibilities when there are 6 in a room. Well, that's 4C1. We just got to go, well, which room would have all the 6 people? 4 rooms to choose from. What else do I have to take away? Well, there's also the possibility that one of the rooms has 5 people in it. That's not allowed. That's going to be 4C1, 6C5, 3C1. Why? Well, first thing I'm doing is I'm saying, well, which of the rooms is going to have 5 people in it? Once I've done that, I've got to go, well, hang on, who are the 5 people that are going to go in it? So 6C5. That leaves me with 1 person. All right, you got to go find a room, but now you've only got 3 rooms to choose from because the other 5 are in that one. 3C1. 72. And that pretty much covers all the possibilities that we're not allowed. So we use the complementary event idea, take it away from 4,096, and we have 4,020 possibilities. They did a bit better that year. 15% of the state got that one right. But the thing about question 10 is it's multiple choice. And that always blows my mind when less than 25% get a multiple choice question correct, because if you think about it, there's 4 options. So what we're basically saying that year is, hey, forget about the question, just guess. You would have done better, because you've got a 1 in 4 chance of getting it right. Alrighty, 14E, let's play with some more questions.